Welcome back to Common Core Algebra II. Today's notes are on 6.9, Modeling with Quadratic Functions. Now, I love this section because it talks about real-world applications of when things are fired, when things are thrown. Sometimes think about if you throw like an object that floats into water, it heads down, then it comes back up. So it follows that path of a parabola. And the same thing happens when you fire something into the air. Those of you who have physics, you were out back just not too long ago firing rockets whose projectile followed that of a quadratic equation. So that's what we're going to talk about here. And just being able to visualize what's happening is half the problem. So in exercise 1, an object is fired upwards with an initial velocity of 112 feet per second. Its height in feet above the ground as a function of time in seconds since it was fired is given by the equation h of t equals negative 16t squared plus 112t. So all that stuff says ahead of time about the velocity, about the function of time, about the seconds is just setting up the equation. So right here, all of that, all has to do with this. But think about what's happening. All right, it says sketch the general curve of the equation. So what you're basically doing is you're doing something that looks something like this, right? Now, we'll get a little bit more exact in just a moment. So, but it asks at what height was the object fired? So what is it asking for? Everything that we learned with our literacy comes back to this. Flip the question. At what height was the object fired? So basically, we're saying that somewhere, and just like in the physics, that we did not actually fire it from ground level. All right, we had some point where we fired it. Now that's a really bad y-axis. Let me see if I can move it over. I can a little bit. There we go. All right, so at one point we fired it and it's above the ground. So what they're asking for here, and like I said, flip the question. They're asking here, what is the y-intercept? So we know the y-intercept is when x is equal to 0. But if you should also remember, it's also when what our constant is. Now, in this case, we have no constant. So everything I said was a lie to you, although I didn't really realize that I was saying it. This was actually fired from the ground. So wherever this happened, it actually was sitting on the ground. All right? Because at x equals 0, or in this case, in our example, t is equal to 0. So you get negative 16 times 0 squared plus 112 times 0, which is equal to 0. All right, so remember at 0 feet is where it was actually fired from. So we talk about this. So now we can say this is actually going to be my x-axis. All right, so C says algebraically, find the time that the rocket reaches its greatest height and the maximum height. So again, what are they asking for? What are they asking for? I'm going to remind you, this is our t, and this is our h of t. H of t represents our height, and if you need to write all over your paper, do that. T is your time in seconds. I believe it's seconds. It is. All right. So what it's asking for is our maximum. So we have h of t. Let me write the down before I lose it, minus 16t squared plus 112t. So now it tells us algebraically. So just like in the last lesson, to find something algebraically, you have to do it using your axis of symmetry. So I know my axis of symmetry is negative b over 2a. So our a is negative 16. Our b is positive 112, and our c is equal to 0, which we don't need. So it's equal to negative 112 divided by 2 times negative 16, which equals 7 over 2. All right, now remember, our x is our time. So that's going to be, in this case, it's 3.5 seconds. All right, or you could leave it as 7 over 2, but in the context of this, I think 3.5 is more accurate. You don't say, how long does it take for the rocket to reach its maximum height and say 7 over 2 seconds? You'd say 3.5 seconds. All right, so always try to make sure that you're thinking about it in the context of the problem. So now to find y, we're going to write down our equation, and I'm going to leave out the t that I can put in my 3.5. And then I do that and I get 196 feet. So here I would say, I would take a minute, even though this is my answer, I would take a minute here and say the rocket reaches its greatest height at 196 feet. Please don't leave out the details, okay? Now it says algebraically determine the time when the rocket reaches the ground. So what is it looking for? Time when it reaches the ground. Well, it starts at the ground. I don't think they want this one. I think they want this one. So they want one of the zeros. So they don't want the 0, 0 because that happens to be the first zero. It wants the second zero. So again, you have to do this by factoring it, just like in our previous lessons. So we have negative 16t squared plus 112t. Always, we're going to set it equal to 0. And you can put it on this side if it bothers you over here. All right, so look for that GCF. All right, the greatest common factor in this case is negative 16. And I can pull out a t. That leaves me with t minus 7 equals 0. So again, I know negative 16t is equal to 0 because I knew this already. I know t is equal to 0, but the other one is t minus 7 equals 0. So t has to equal positive 7. Now, if it was equal to a negative number, time cannot be negative. So please make sure you're making sense of this. All right? And it says label it on your graph. So don't forget that part. So my graph right up here is going to be 7, 0. All right, again, answer the question. What does it say? Determine the time when your rocket reaches the ground. In 7 seconds, the rocket reaches the ground. Make sure you're writing it down. These are fun. You're going to think they're fun too. All right, pause if you need to. Otherwise, I'm moving on to exercise 2. All right, a skateboard half-pipe ramp has a shape in the form of a parabola whose equation is y equals this. So I know I'm not big into skateboarding, but even I know that it looks something like this, right? There's usually a ridge on both sides of it. All right, where x represents the horizontal distance across the 20-foot wide half pipe, and y represents the height, the ramp's height above the ground in feet. All right. So with the help of your calculator, sketch the graph of the half pipe below, label its height and its endpoints and its minimum point. So if we put this into the calculator, we can get that information. All right, this point down here is the point 10, 1. This point up here is the point 0, 7. And this point over here is 20, 7. Okay? Now, how did I know it was 7? I didn't really talk about that, did I? My apologies. I know it was 7 because my y-intercept right here is positive 7. So I know that when I'm doing this, it looks something like this. This is 10. Not really drawn to scale, my apologies. And this is 7. So at 7, I wanted to know what my x values were, and the answers were 0 and 20. All right, so that all comes off my calculator. Nothing really exciting there. So label its height and its endpoints and its minimum point. We did it. That's all we needed to do. All right, so that was not hard. Again, the hardest thing here, and it's the part that I forgot to tell you about right from the beginning, is to know that the y-intercept, which basically means it's got to be where that half pipe starts, is at 7. Okay, so when I went to my table, I looked to see when my y was 7, what happened to my x. Remember, 10, 1 was my vertex in the middle, and then I had a 0 here, and I had a 20 here. All right, so if you have any questions about that, let me know and we'll put it into our calculator and take a look at it tomorrow. Moving on. Okay, exercise 3. The crazy Caramel Corn Company has determined that the percentage of kernels that pop rises and falls as the temperature of the oil the kernels are cooked in increases. Obviously, it modeled this trend using the equation. So it looks very complicated, but remember, it's still just a quadratic. All right? P represents the percent. So again, this is your paper. Mark it up. This is the percent. And the kernels popped, and T represents the temperature. So T represents temperature of the oil in degrees. Okay, temperature in degrees Fahrenheit. That's kind of important. So algebraically determine the temperature at which the highest percentage of the kernels pop. Also determine the percent of kernels that pop at this temperature. So what are they asking you for? All right, the highest percentage. So remember, percentage is your P. Remember, this is going to be a point. It's going to be T, comma, P. I like to kind of put things together with my X's and my Y's. So my T is my independent variable and my P is my dependent. So what it's asking for is what is going to be the maximum? Because this is going to, I know this is, I'm sorry, this is going to be a opening downward. So we're going to have a maximum point here. All right? So I know it's going to look something like this. So what they're asking for is this point right here. And it's asking you to tell you in terms of the percentage and the temperature. Okay? So that's what we're looking for vertex. And look for those key words like maximum, highest, lowest. If it opens up, you're looking for minimums. So now if they're telling you to do it algebraically, we know we have to use our equation, x equals negative b over 2a. All right, now b is 2.8. Okay, so a is negative 1 over 250, kind of a crazy number. B is 2.8. We don't need c for this one. So it's going to be 2.8 divided by 2, it's negative 2.8, 2 times negative 1 over 250. And surprisingly enough, when you put this into your calculator, you actually get a pretty nice number. You get 350. Now remember what that represents. I have x equals, but remember in terms of this, this is really T. All right, it's our temperature. So it's degrees Fahrenheit. So now what do they want to find? They want us to find the percent. So based on that, we're going to use our P is equal to negative 1 over 250. And instead of x, we're going to use the temperature of 350 degrees squared plus 2.8 times 350 minus 394. And when we're all done with that, again, we put the whole thing in the calculator. We don't try and do this in our head, and we get 96%. All right, again, I don't have an awful lot of room here, but if this was a test or a Regents exam, I would spend some time writing this down. Use the vocabulary from your equation. So I would say the temperature at which the highest percent of kernel pops is 350 degrees. The percent of kernels that pop at 350 degrees is 96%. I just use the vocabulary from the question. I don't try and do anything too fancy. So using your calculator, sketch a curve below for p is greater than 0 and label your window. For example, what they're saying here is somewhere along the lines, I'm going to have someplace where it starts and it ends. And I can get these points from my calculator. Remember, these are my zeros. It's when this is 0, my y's are zeros. So this one is going to be 195. Again, right off our calculator, this is going to be 505. And we determine that our point right here is 350, 96. All right, so sometimes doing that first is a little bit helpful. So C, now I just put that information in. I got the whole thing off my calculator, and this says that using the 0 command, and that's what I used. Or you could just look at your table, because these numbers are nice integers. All right, so you can see it, but you can see they're big numbers. So sometimes using the 0 command might be easier. All right, D says, if a typical batch of popcorn consists of 800 kernels, how many does the Crazy Caramel Corn Company expect to pop at the optimal temperature? Well, what did we say the optimal temperature was? Did we say that? Yes, of course we did. We know at 350 degrees, we get 96%, right? So if we have 800 kernels times 96%, and remember, we don't deal in percents, we deal in decimals, 0.96, and we get 768 kernels. So a typical batch of popcorn of 800 kernels at 96% is 768 kernels expected to be popped. All right, now E. For a batch of popcorn to be successful, the company wants at least 85% of its kernels to pop. Write an inequality whose solution represents all temperatures that would ensure a successful batch. Solve this inequality graphically to the nearest degree and show your graph to below, I think it's a little bit of a typo, labeling all relevant points. So show your graph below, labeling all points. So basically, all they're asking you to do here is to take our original equation, which is negative 1 over 250 t squared plus 2.8 t minus 394. We want that to be greater than or equal to 85%. Now, I'm going to use percentages here. I'm not going to use 0.85 because it's telling us to do it in terms of percentages. All right? So it says write the inequality, and it says solve the inequality graphically, which means we're allowed to use our calculator. All right? So if we take a look at this, let me just pull it back down. So this is what we have, right? So basically, what we're doing is we're considering what this looks like graphically, which means we know where it starts and we know where it ends, right? Based on the graph that we had up on top. But at 96, so at this point here, we know this is 96%, right? And they're saying they want to know 85%, which we'll put down here. They want to know 85%. So we're going to have two possibilities here. All right, now you can use your calculator for this and determine when y is 85, what's my x? All right, if I tell you to do it graphically, I'm assuming that these are going to turn out to be nice numbers, and they are, because this one turns out to be 298, and this one turns out to be 402. All right, so we know it's going to be between 298. Again, we have greater than here. All right, it has to be greater than. So we know it's going to be between these 2 points, t less than or equal to 402. All right, so in other words, what they're saying is the optimal then will be between here and here. Okay, and by the way, these are degrees Fahrenheit. So that last one was a little tricky, but everything else just translated into what part of the graph they're looking for. All right, you may need to rewind this one and take a look at it again. And please feel free to do that. Really understanding these before you come into class is the objective here. The objective is not to write everything down. It's actually to take time and try to internalize it before coming to class. Okay? So as always, my darlings, make good choices every day, and I'll see you tomorrow.